Yes, so this is a very important concept of limits, and I know that in your class 12th you will start from continuity because derivatives you have already done. But see, if you can recall, then everything in derivative was simply based on a single concept of limit. So unless and until, see, you don't understand the rigorous definition of limits, you will find really always on a very shaky wicket. So today, though it has hardly much to do as far as your examination of board is concerned, but one thing I can assure you, that if this concept of limit you can understand today, then see, it will go a long way in making you understand all the concepts, majority of concepts in higher mathematics. Because if you look in the syllabus of class 12, then see, the next two chapters will be of continuity and differentiability and application of derivatives, then integration. Integration is nothing but inverse of differentiation, and differentiation is based, as I said, on limits. So understanding this concept of limits is very vital. So without taking much time, I will take it up. So before I take this concept of limit, let me explain you something about, give you some idea rather of nearness and farness. Now see, suppose suppose you say that your school is only 100 meters from your residence. Then normally in day-to-day life, what the conclusion generally we would like to make is that yes, you are residing very near to Vidyalaya. Very near to Vidyalaya. But then see, if I tell you that go and procure this some book from say this bookseller who is just outside the gates of Vidyalaya, then he will be more nearer to it. But if I say that you go in the staff room and tells a particular teacher something, then see, the staff room is much more nearer. And if I say that you go to the adjoining class then of your 12th, and there you call a particular student, then that would be more nearer. And then suppose I say, then if I ask you what is the distance between two students sitting in your class on the same bench, then see, it will be almost say in feet, say 1 feet or 1.5 feet. So point is that this concept of nearness and farness, they are relative one. They are relative one. For example, if suppose a cat is jumping towards a pole, suppose, and he is only say 0.3 meters away from it. So 0.3 meter, you can well understand it's a fairly small distance. But then see, if I say 0.3 meters, and then I say now the distance is only 0.03 meters. Then in comparison to 0.03 meters, this 0.3 meters will be a fairly big distance. Likewise, suppose 0.03 meter, you know practically it's a very small distance. Now if I say 0.0000 followed by say 5 zeros or 6 zeros and 3, then in comparison to this number, this 0.03 is a fairly big number. So point is that see, in mathematics there is nothing like we are very close to something. Because suppose this 0.00, how many zeros? 3 and 3, 6, 7 zeros, 3. You know it's a very small number. But then given to this small number, we can still think of a number in comparison to which this number becomes fairly big enough, fairly large. For example, point and 0 zeros, 100 zeros if I write. Then in comparison to this number, this point 0.703 will be a fairly large number. Now, in comparison to this, suppose I think of a number 0.00 followed by 1000 zeros and then 3. Then see this number, earlier thought, which is 0.103, that will be a fairly large number. So, point is that there is no end up. There is no end up to any small number. Suppose I write points, a billion zeros 3. It's a fairly small number. But then still I can think of point, suppose I write 10 raised to power billion, 1 billion zeros. After point I am writing 10 power 1 billions. And then 03. Then in comparison to this number, this earlier number thought of, which is 0.1 billion 03. So that number becomes extremely large number. The essence of this whole thing is that no number in mathematics can be said to be very near to something. Because you think of any number, in comparison to this number, you can again think of a number in comparison to which the earlier thought of number becomes extremely large. So point which I am emphasizing to you is that there is no end up in mathematics. You can think of any small number, howsoever small, howsoever negligible, but still you can think of a number in comparison to which the earlier thought of number becomes extremely large. So nearness and similarly farness, because suppose you say that something is too far away, say 10 raised to power 6 miles away from here. Then if I say 10 raised to a billion, then see, in comparison to 10 raised to a billion, the earlier number 10 raised to power 6 becomes, too small. So both these concepts of nearness and farness, they are relative one. They are relative one. There is no end up. So this is one thing which you will bear in mind while understanding the concept of limits. Now after this brief introduction of, see, I forgot my duster. Let me quickly bring it. Yes. So after this concept of farness and this nearness, I will come to what actually you have learned in class 11 as far as limits are concerned. You take an expression x square minus 9 upon x minus 3 and limit x tends to, suppose you write 3. What does it mean? See, here actually, see, first I will tell you how you have done actually in your class 11. Then slowly and gradually we will be coming to the geometrical definition of limits, and then the most theoretical and most desirable definition of limits in mathematics, which is given in terms of epsilon delta. See, once again I tell you, this is not in your course, but if once you understand it, then see, things will come very easy to you, because understanding this concept of limit is too vital for you people to understand in its depth. So, yes, now suppose this expression. Now this expression in class 11, you must have done like this. You must have said that just limit x tending to 3, and then see x, this thing tending to x minus 3, x plus 3 upon x minus 3, and this goes and this becomes x plus 3. So if you assign x value say 2.99, then the functional value, suppose this fx, what is the function? X square minus 9 upon x minus 3. This functional value will be 5.99. 5.99. Suppose you are coming further closer to this thing, 3. suppose 2.999999, suppose 6 nines, then functional value will be 5.99969. So if x is say 2.999900 times, so here what the thing will be, your functional value could be 5.9999900 times 9. Fine. Now here see, you are approaching 3 from two sides. 3 is a number on your real line. Suppose this is 0 mark, 1 mark, 2 mark, 3 mark. 3 you can approach from this side as well as this side. You can approach from both the sides. And what you will notice is that whether you are approaching it from the left hand side or from the right hand side, from the right hand side if you will approach, then what the number will be? 3.01. Functional value will be what? It will be how much? 6.01. If it is 3.0000001, say 5 zeros or 6 zeros, then function will be 6 point that many zeros, 6 zeros and 1. So likewise, if it is 3 point say 100 zeros and 1, then it will be 6.100 zeros and 1. So this is how. So what you are observing actually is that as you are approaching the number 3, here, then your functional values, they are approaching the number 6 either from left or from right. So now this concept of approaching the number 3, this is precisely, see, in a way, see, if you just want to understand the limit, it is fair kind of. That yes, what should happen? That under the limiting condition, two things which you will bear in mind is that one thing is that the number will never be equal to 3. Please see that this x tends toward 3. It means that x will never coincide with 3, or in other words, x will never take value equal to 3. But then it can come nearer to 3 to any degree whatsoever one pleases. To any degree whatsoever one pleases. Now you can be nearer to 3 to any degree. Now it is your choice that how much nearer you want to be. But then you will never be equal to 3. That's one thing in the limit which should be very clear in your mind. And the one classic example for this particular understanding of limit is that we say that suppose a cat is jumping towards a pole, and on each jump the cat jumps almost half the distance between herself and the pole. Then in how many jumps will the cat be able to touch the pole? The answer obviously is infinite jumps. The cat won't be able to touch the pole for the reason, suppose the distance between the pole and the cat is 2 meters. Then on the first jump it will travel 1 meter. Then on the second jump it will traverse how much distance? Now 1 is the meter is the distance between the pole. So 0.5 meters, and then 0.25 meters, then 12.25. So half of this, that is on each subsequent jumps, the cat is traversing it lesser distance, exactly half of the distance which the cat has jumped in a previous jump. So this process will keep on continuing, and the cat will never be able to touch the pole. That's the thing. So this is one example for making you understand that yes, under the limiting condition, whenever a number tends towards 3 or whatever, in general, suppose x is tending towards a number small a, then x will never be equal to a, but x can come nearer to a to any degree whatsoever one feel likes. And as I said, that nearness and farness is a relative concept. You can't say that you are very near to it, because when you say, when you tell a number that yes, this is a number and it's a very small number, then still you can think of a number in comparison to which the earlier thought of number becomes too large. This particular aspect we have already dealt with. So point was like this, that in limit what actually is happening? That this is your function. This is your function. So what you are noticing is that when your variable is approaching towards some number, is approaching towards number, it is not coinciding with that number, then what is happening? If the functional values, they are also converging towards a fixed number. In this particular, the fixed number is 6. See, whatever, when you are approaching towards 3, then your functional values, they are heading towards or converging towards a fixed number 6. Because as you are coming more nearer, the distance between 6 and that functional value becomes more and more smaller. And see, this point I will repeat again. See, what I am saying is that when your this x tends to a particular number, say a, right now a is here 3, then what is happening? What you are observing, that functional value is approaching towards the number 6. It is converging. The functional values are converging towards a number, a particular number. And the more nearer you come toward to 3, the more nearer the functional value becomes towards 6. That is to say that the difference, that the modulus value, this modulus value of 6 and functional value, minus functional value minus 6, that becomes smaller and smaller the more nearer you come to 3. And when see this thing takes place, that is when your this variable approaches or tend towards a given number, and if the functional value they also converge towards a fixed number, then you say that yes, the limit exists, and that number toward which the functional value converges, that is better said to be the limit of this thing. But then I said that maybe that to some extent, to some nearness, the number may be converging, but eventually, see, if you look in, the number may diverge. The number may not be able to converge towards a fixed value. For example, see, if I take this thing, one example here I am taking where the functional value will not converge towards anything, and that example would be the functional, okay, let me write it. Okay, suppose I write my function to be sine 1 by x, and I say to find limit x tends to 0, find x tends to 0. You have earlier seen the graph of sine x. Now see here, you may come nearer to 0. But then this sine 1 by x, what you will find that this value will never converge towards any number. It will rather fluctuate between plus 1 and minus 1 for the obvious reason that, see, what is the graph here? The graph of sine x is like this. It goes for like this thing ever. Between plus 1 and minus 1, it will keep on varying as you go towards infinity. When x goes to 0, 1 by x will tend towards a very large number. So see, the idea is that the more nearer to you come to 0, then this functional value sine 1 by x will not converge, will not be converging towards a definite number. Rather, what it will be? It would be always varying between plus 1 and, or fluctuating between plus 1 and minus 1. So this is one example where the functional value, this function will not have the limit. For the obvious reason that functional value, they are not heading towards a fixed number. For limit to exist, what should happen when you say that when our variable approaches a definite number? Here the definite number is what? 0. So functional value should also converge towards a definite number. So here see your this thing, it is not converging towards a definite number, rather it is varying between plus and 1 and minus 1. So in a way, what you will say that here the limit doesn't exist. So the second thing which is more important and a essential characteristic of limit to exist is that whenever your variable is approaching towards a definite number, then your functional value should also converge or tend towards a fixed number. So that's the second point which needs to be taken care of, because here I have given you a counter example just to make you people aware that yes, that for limit to exist, the functional value should converge towards a definite specific number when x tends towards a fixed number. So see, initially you may find somewhat difficult to understand, but I can assure you that things are too simpler. Things are too simpler if you show a little bit of mental alertness at this juncture. I am more than sure that you will understand the things in its entirety, and that will pay you a lot in understanding the higher mathematics. So with this, once again, I end up that for see, still we have not come to the rigorous definition of this thing. We will come later on, but this is how you had been till now in your class 11. Till now, how you had been actually being told that yes, what this vague idea about the limit must be persisting in your mind, must be like that only. That yes, so limit, if I say in general terms, limit x tending to a fx is equal to L. So what the idea was in your mind, students, was that when your this variable is coming nearer to a, so idea is your functional value should be heading towards L. Heading towards L. Now see, this thing that x is coming towards a and functional value is converging towards a definite number L. Now see, we had to mathematically define this thing in a manner so that it satisfies the mathematical principles. Because still we can't say that how much near we should go so that we are in a position to say yes, now we can declare yes, the number is because see, practically we can't say we can come nearer to it to any degree. So see, we can assign any small number to a and suppose it is approaching towards L till that number. Maybe that after that the behavior of the function may change. You can't say. You can't say. So that important aspect, that how practically we can assign some criteria, that yes, how we can actually declare that function will be heading towards a definite number L when your variable approaches towards this number A. So this thing we had to now really quantify so that yes, we can declare in that particular manner yes, that this functional value is always heading towards the L. So this thing we will today try to mathematically define in a rigorous manner. Earlier, otherwise, see, you were just being told yes, it is. And as I said, you cannot practically check it. After all, see, maybe that x is approaching towards a. Suppose x is a minus 0.000, say 10 billion zeros and 1. Till that, see, you are finding that your functional value is coming, say, towards, say, between L and L minus point that much billion zeros 1. Okay, so till that you have checked it. Now nobody practically can really check it for billion zeros 1. Even the best of supercomputers will find difficult to give you that much of result. And see, somebody can say that yes, no, the functional value will not be heading towards L after say 10 raised to power billion zeros. Somebody makes a contention of this nature. Then see how we can satisfy someone, because this is a non-ending process. And this is, see, actually what needs to be taken as a challenge. And this challenge we had to redefine in terms of mathematical rigorousness. So before I come to the actual definition, I will be now giving you two more terms which needs to be defined, and those two terms will be yes, write down neighborhood, NEIGH, neighborhood of R, small r, and R is a positive number. R neighborhood of number A, A. This thing we will be writing as N capital R and within brackets A. This is with the symbol for writing is NRA. Now, this is here. Remember, and that R is greater than 0. Whenever we are talking about R, then R is a positive number. And by neighborhood of R neighborhood of A, we will simply mean here that suppose 0 is here, A is any number. It can be on the right side, it could be positive, it could be negative. Suppose A is here. Then by R neighborhood, we will simply mean that this is A plus R mark, this will be A minus R mark. Then the open interval, please understand it. A minus R, A plus R, comma, is called R neighborhood of A, NRA. Please see, this is the definition. That on the number line, if you consider this open set A minus R to A plus R, so that we will be now referring as R neighborhood of A, and R will be a positive number, and A will be and R will be a positive number, and A can be any number on your real line. After this R neighborhood of A, we will take another definition here, and that will be deleted write down deleted delta neighborhood of A. Deleted delta. This is a Greek word, and delta will also be a positive number. Deleted delta. Please write down deleted delta. Neighborhood, I will be writing short as NBD, neighborhood of A. This will be denoted as N delta A, and from it, see, this is the open. This is basically the delta neighborhood of A, and from this delta neighborhood of A, if we see, remove certain elements, like suppose we have removed the this middle element A, then this set, open interval, this delta neighborhood of A minus certain elements of the sets, then that set is called deleted delta neighborhood of A. Deleted delta neighborhood of A. So what is the definition here? A from delta neighborhood, this is the Greek symbol, you know it, deleted delta neighborhood of A, certain finite elements are deleted. Then such open interval, then such remaining open interval, then such remaining open interval is called open delta neighborhood of A is called deleted delta neighborhood of A. So N delta A minus certain elements. So here we can remove more than element, but in our this analysis of limit we will only be removing the middle one, that is A. So basically what the thing is, here you have 0, suppose A is now here, so A minus delta, A plus delta will be these two marks, and in from it, see this number, A number, you remove it, then this remaining interval will be called as deleted delta neighborhood of A. So now see, with these two terminology, and mind it here, whenever we are talking about R neighborhood or delta neighborhood or any neighborhood, then all these R, delta, epsilon, they will be positive numbers, because see, you can understand with the general. Delta neighborhood means all those elements which are at a distance of this thing. And one more thing I would like to explain before I proceed with my geometrical definition of limits, and that will be, yes, geometrical interpretation of inequality. Geometrical interpretation of inequality. Right now, geometrical interpretation of this mod x minus a, mod x minus a. Okay, yes, this point needs to be understood, what we actually mean by geometrical interpretation of mod x minus a. So here see, it's a geometrical meaning I would like to make you plain clear, that see x minus a is nothing, but it will give me all this interval only. What if this is a, this is suppose 0, then a, your x will lie there, mod x minus a is less than r, Its meaning I have to explain it to you. So see, it simply tells you the geometrical interpretation of this modulus inequality is that all such numbers which are at a distance of r from a, which are at a distance x minus a is less than r, means all such numbers on the real line which are at a distance r from a. So obviously what it is, on the left side it will be a minus r mark and it will be a plus r mark. So effectively this inequality is nothing but this gives you the open interval a minus r to a plus r, or in other words it is this inequality gives you the the r neighborhood of a. R neighborhood of A. So see, in your this class 11th, you must have come across this sorts of inequalities. Mod x minus A is less than R. So the geometrical interpretation of this thing is that yes, this inequality simply tells you all such elements which are at a distance. X minus A means a distance from A, that should be less than R. And please see, this r will be positive number, for obviously modulus is always a positive number. At the best it could be 0, but here see it is always a positive number. So here, that's the thing. So it will be a minus r to a plus r, all such numbers. Yes, so that thing you had to ensure. Now on the same basis, if I ask you what is the number x plus 3 is less than 7, you solve this then what you will do? You will simply try to bring it in your standard form. You will write x minus 3 mod is less than 7. So point is that this is number 0. This is okay. Let me make it here. This is your real line. This is your 0. This is your mark minus 3. Suppose 1, 2, 3. This is mark minus 3. Then what is this? The distance of x from minus 3, because x plus 3 you can rewrite as x minus minus 3, so as to bring it in your standard form. X minus a is less than r. So you will say that minus 3, see 7 points here, 3 here, so it will be 4 here, isn't it? And here it will be how much? Minus 10. So this open interval minus 10 to 4, that is the solution of this thing through the geometrical interpretation. So students, please do remember this thing. This will again be too much pain for you. So with this understanding now, we now take up our definition of limits. The standard definition, which is better known as epsilon delta definition, which is better known as epsilon delta definition of limits. है ना? Epsilon, you know, it is denoted like this, and delta is like this. These are Greek terms, and epsilon is all, and both of them will be positive numbers. Both of them will be positive numbers. So this much of information is prerequisite for understanding your limits. Let me have a little bit of water so that yes. Yes. Now, please remember, I will be making use of these two terms frequently. Now, see, I am giving you first a definition through which you can understand this concept of limit geometrically, and that will be, I think, more easier for you to understand, for the simple reason that things will be explained in terms of this geometrical visualization. So you say, we say, now see, we say that, we say limit x tending to a fx is equal to n. Fx is equal to n. If, now this is a symbol what? For every. If, for, first you write down, if for every epsilon greater than 0, there exists, this is the symbol, there exists, this inverted V means there exists. I am writing here because now I will be using this set theoretical language. So this is this symbol for every, if for every epsilon greater than 0, what should happen? There should exist a delta greater than 0, and then what else? Please see, such that. This symbol is for such that. Right now, next time I will not write. This inverted, tilted epsilon is such that. Okay, such that, what should happen? Such that mod fx minus L, this thing, should be the element of such that fx minus L is less than epsilon. Yes, is less than epsilon. See, first let me write the geometrical definition such that fx is the element of what? Epsilon neighborhood of L. Fx is the whenever, please see, this wording will be whenever x is the element of deleted delta neighborhood of A. And this thing, which number you are excluding? A. In this deleted delta neighborhood, what you are doing, this thing deleting minus A. Okay, so this is the geometrical definition. I know, see, at the first instance you will find something very odd. But see, I will tell you repeatedly a good number of times, and I will make sure that each one of you do understand it in its right earnestness. Okay, so now please see. First you write it, and see here a slight change of word will altogether change the meaning. This is a very standard definition. I read it for you. We say limit x tending to a fx is equal to L. If for every epsilon greater than 0, I will explain you. First, I will tell you what is the definition. If for every epsilon greater than 0, there exists a delta greater than 0 such that fx belongs to this epsilon neighborhood of L whenever x belongs to deleted delta neighborhood of this thing. Or deleted delta neighborhood of A. So now please see what it means. It means that, see, now please, one thing is here. If for every epsilon greater than 0, please here also write howsoever is small. Please just here add the word howsoever is small. This is important, howsoever is small. Now epsilon here will remain positive, but then see you can give any small value to it. Now it is up to you. This value of epsilon you will give. Now this can be given any small value, and this small value will entirely your discretion. It will be something of your choice. But then what should happen? Whenever see you have once assigned a particular small value to epsilon, then what should happen? Then there correspondingly there should exist one positive number which we are calling delta, and this positive number delta should be such that when x lies in this neighborhood of A, in deleted delta neighborhood of A, deleted delta neighborhood of A will mean what? See, I will draw two lines here. Here this is my 0, this is my 0. Suppose my number A is here, and my deleted delta neighborhood will be what? A plus delta mark here, A minus delta mark here, and from it I will take out the middle number A. So my deleted delta neighborhood is what? A minus delta, A plus delta, and from this set I am excluding the point, the middle point A. So this is my deleted delta neighborhood, which I am denoting by n delta A minus A. Symbolically. But it is an open interval. It is an open interval. But then what should happen? Now what I say, see, whenever x belongs to this deleted delta neighborhood of A, in this interval, whenever x, then now suppose L is a positive number, then L should fall wherein? Between L plus epsilon and L minus epsilon, in this interval. And this interval is what? N epsilon L. N epsilon L. N epsilon L is what? N epsilon L. Epsilon neighborhood of L. So it is the interval what? L minus L, L epsilon, L plus epsilon. On the real number line, see, L suppose is a positive number, A suppose is a negative number. So what your definition simply has to say is that, see, you assign any small value to epsilon. That is, the number which you are claiming that to be your limit of your function, that is L. See, now you can take around it, you take any small epsilon interval. Now it is up to you. Epsilon you can give value 0.01, you can make it further small, you can make further small. So epsilon you can give whatever value. Then see a corresponding delta, then see what should happen. It is up to you. You around this L, you think of a very small interval. It is up to you. Once you have given a particular value to epsilon, then what the thing which you have to look in for is, yes, that there do exist a corresponding deleted delta neighborhood of A. Means around A you should find some positive number delta, such that in that deleted delta neighborhood, that is A minus delta, A plus delta, and the middle point excluded, this is what the deleted delta neighborhood exactly means. So what should happen? That whenever x will belong to this deleted delta neighborhood of A, then functional value will always lie in the epsilon neighborhood of L. So if this thing is happening, now see, then you can say that your functional value, that the limit of your function is L. I will repeat again, because see what the thing is, that here see, if you look in, that what you have to do it, that the number which you are claiming to be your limit, suppose L. Now about L could be anywhere on your real number line. See, this is your one number line, this is your another number line. So on your this L, you take any number. Suppose I have given suppose epsilon value 0.0001. So suppose this is the mark here, this is the mark here. This is L plus 0.00001, 301, and this is the mark corresponding to L minus 0.001. So initially you had to give some value to epsilon. Please see, initially what you had to do, you had to give some value to epsilon. Now it is howsoever small you can give it. It is perfectly up to your choice. Your choice. You can think of any small number. You can say epsilon is point, say billion times 0 is 1. Then see, okay, we have chosen such a small epsilon. Then see what should happen. Then corresponding to this particular specific value of epsilon, if you can find a corresponding value of delta, or in other words, you can find a deleted delta neighborhood around A, that is a interval A minus delta, A plus delta. That is, you are a delta, a number delta, a positive number delta if you can find, such that within this, whenever your x lies in this deleted delta neighborhood of A, then functional value falls within this epsilon neighborhood of L. In epsilon neighborhood of L. See, if this thing is happening, and if this thing is true for all the values of epsilon, howsoever epsilon, it is not that once you have chosen a value, then it is end of the things. No, you can choose epsilon whatever you feel like, howsoever small. Once you have chosen point, say billion times 0, 1, then next time you say I want to choose point, say 10 raised to power billion zeros and 1. Then again see, you had to show that yes, still there exists a positive number delta. That is to say, you still have to show that there exists a deleted delta neighborhood of A. Deleted delta neighborhood of A means what? You have to find the interval, open interval A minus delta, A plus delta. Of course, from that you will exclude the middle point A. So whenever x takes any of the value within this deleted delta neighborhood of A, then your functional value automatically will fall therein. So this is the idea. And this is, now see here, you can't say that we are coming so much nearer. See what it, I repeat, it essentially says that for every value of epsilon, what should happen? There should exist a corresponding delta, another value delta. And this delta should be of what nature? That within this deleted delta neighborhood of A, the functional value should automatically fall within the epsilon neighborhood of L. So see, if for every epsilon such a delta is existing, then see, you can safely say that your limit of function is L when x is approaching towards A. So this is the geometrical interpretation. See, at the first this thing, I once again would like to remind you that you may not be able to get it. But then see, simple idea, this idea you have to remember it. Because here it is very, practically it is saying, what essentially it want to say is, that what you used to say that we are coming closer to A, then functional value should come towards L. So that was a layman language. That was a layman language. With all mathematical rigorousness, this is the correct mathematical definition. This is geometrical definition. And what the geometrical definition is, that see, for every epsilon, now it is up to you, that you will choose some epsilon neighborhood of L. Epsilon neighborhood of L you say, or you say simply that you are choosing A minus L and A plus L. Because epsilon neighborhood of L is nothing but what? L minus epsilon, open interval L plus epsilon. They are same thing. They are representing the same thing. Both are the same thing. Either you say epsilon neighborhood of L, or you say open interval L minus epsilon to L plus epsilon. They are the same thing. Either of the terminology you can make use of. So what I am saying is that first, if your contention is that functional value, that the limiting value of your function when x tends to A is L, then what you need to show is that whenever you are taking a epsilon neighborhood of L, L is what? The number which you are claiming to be limit. Then see, you should be in a position to always show that there do exist a deleted delta neighborhood of what? A, where this variable is approaching, and such that whenever x is belonging to this deleted delta neighborhood of A, then functional value should fall within this epsilon neighborhood of L. So if this thing is happening, If this thing is happening, then see, you can safely make a contention that limit x tending to fx is L. Fx is L. Now I take two simple examples here which will make this definition clear. But here once again, see, I would like to caution you all that see, you can't change the wording even slightly. This is delta that we say limit x tending to a, fx is equal to L, a if for every epsilon greater than 0, howsoever is small, then what should happen? Once you have chosen an epsilon neighborhood of L, then there should exist a delta greater than 0 such that fx should fall where? In the epsilon neighborhood of L whenever x belongs to deleted delta neighborhood of L. That's the definition. And this is better known as, this is the geometrical definition. We will later on come back to this theoretical definition, of course implying the same meaning. But then see, there we would be making use of different, this modulus, symbols that we would be making use of. Instead of geometrical, we would be moving towards this modulus inequalities. So I wish that today you have this thing, but once again I repeat, see, the only way out is, I'll be taking two very good examples here, and then I will show you, yes, that how actually you are convinced that, see, you take any this epsilon interval of some of the number which you are claiming it to be your limit, and then you are showing that yes, actually there will exist in positive number delta such that within that deleted delta neighborhood of A, whenever x falls within that deleted delta neighborhood of A, then function value will fall within this epsilon neighborhood of L. So this is one thing. So I quickly come up here. I think I have given you a fairly rigorous definition here, and then the standard definition which you need to know, and based upon this thing, see, I will show you that how we actually are in a position to say, yes, that why this limit of such and such function is such and such thing, that thing is more important, because see, now your age permits, because you had to take up problems here for which are competitive, see, this competitive examination demands. So see, once you know the things in the depth, then see, you are very confident. And you can take up the things in the right earnestness. Then see, a little bit of practice and exposure to difficult problems which are asked in the examination, that suffices. And there, see, you have plethora of resources at your disposal where you can find them. So with that understanding, see, today I will show you. Suppose my fx is a constant function, k0, and I wish to show that limit x tending to say a is any number on real line of fx is only k0. Suppose k0 is what? Any constant, where k0 is any real number. Now this is how we have to show it. So essentially what I need to do it, I think first try to understand what I need to show. I will draw two lines. Suppose my k0 is number here. K0 is number here. Say it is, say, minus 3 suppose. I will not write, because see, it could be minus 3, it could be minus 11, it could be 4, it could be root 2, it could be whatever. Any number, because constant function is defined what? Fx is equal to k0. Its graph will be like what? If it is like fx is equal to k0. So if it is root 2 suppose, so you make a right line, so this will be a line parallel to it, constant function. So here there is nothing much to this thing, these graphs you know. So now we will show that limit of y, the limit of this constant function is always same. Whatever x here, a is any number. A, you take any number on the real line, it will always be k0. The reason is simple, because around k0 you take any interval, whatever. Suppose you have taken 4 or 0.4 suppose. So this is say k naught minus 0.4. Then what should be your A? A is suppose this thing. Then I say what is your delta? Suppose epsilon you have given really 0.04. Then what is your delta here? Please try to understand. So delta will again be a positive number. I say you take delta to be any number, any real number, any positive real number. You can take 7, you can take 150, you can take 10 raised to power 6, whatever. Any real number you can take. How, whether large or small, that is up to you. For the reason that, see, any interval around it, this you take it. From A you leave it. And delete the delta neighborhood, then what will happen? Fx will be what? K naught only. So, see, the functional value will always be lying on K naught only. So, irrespective of the fact that howsoever small interval you choose around it, and this around A you take any delta, then functional value will always fall within that epsilon neighborhood of K. Yeah. So that's the classic example where this epsilon this delta will not depend upon epsilon. See, in rest of the cases, delta will definitely depend upon the epsilon. But this is one classic example where this delta is not depending upon epsilon. See, you take epsilon any damn small number, and the delta you take any positive number, howsoever large or howsoever small, that's up to you. This thing will always happen. When you take any number in this large delta neighborhood, and you will find this thing, because all the functional values, they will exactly be on K naught. K naught. So see, howsoever small interval, you make it whatsoever small, but this functional value will always be lying in that epsilon neighborhood of K. So this is one classic example of this thing, constant function, which will give you some idea, yes, how delta is to be found when epsilon has been given to you. So this is what you have to do. And now see, this epsilon can be any number. You can give any small number, howsoever small. But then see what the thing is. If you want to show that limit of your function is K, is L, then around that L, see, you will choose one epsilon neighborhood, and then see, if to correspond to this epsilon neighborhood of L, you will be looking for a deleted delta neighborhood of A, such that whenever your variable lies in that deleted delta neighborhood of A, then functional value should fall here. So this is how we have shown it, and that's the reason. So here, see, what is the thing is, you choose any epsilon and say delta can be any positive real number. So this is one classic example for your understanding of the concept. Now I will take another example here, that of identity function. That of identity function. Identity function. And again here in this identity function, fx is equal to x. This is identity function. We will again show that limit x tending to a fx is equal to what it is equal to A only. So what the thing is here? Again 2 lines. 1 0 1 0. Suppose this is A. You have chosen some A plus epsilon neighborhood of A, because you say that your limit of a function here, when x tends to A, fx, it will be A. So both the limit and this thing are coinciding, no issues. So what the thing is, you have chosen some epsilon neighborhood of, and corresponding to this, what you need to show is some deleted delta. So let delta, suppose epsilon is say 0.01, then let delta also be 0.01. So it is delta and epsilon, you give same values. So here it is A plus, minus delta, A plus delta. So see, if delta is equal to epsilon, then what will happen? If x is lying here, the functional value fx will be what? That will be equal to x, so it will lie here. So any number less than epsilon you can choose this. Any number, let delta 0.01, you take delta to be 0.001. So this will be what? a smaller number. This will be a smaller interval around A. So if your x lies here in this deleted delta number neighborhood of A, then functional value will obviously fall therein because it is a larger interval. This is contained in this thing. This is a subset of this thing. So this is another example where delta will be for a given epsilon. See what your corresponding delta will be, any number which is smaller than this thing. So this is another interesting example where you would be saying that yes, this is our this thing is our delta. Now see, I will tell you that how delta is to be found when epsilon has been chosen or epsilon has been given for numbers whose graph is continuous, whose graph is continuous. See, you must not be still knowing that what this continuous graph actually means. So just now, for till that continuity has not been taught to you, you simply see where there are no abrupt change in the value of the function. Like sin x, it's a continuous graph. Tan x, see, it has got a point of discontinuity wherein between my principal branch it's continuous throughout, but see at pi by 2 or odd multiple of pi by 2, see there is a abrupt change in the value function. On one side it is going toward plus infinity, and on the other side of this 2k plus 1 pi by 2 it is going towards minus infinity. So those points we will be skipping off because yes. So now I will take two more examples here for making you realize that yes, how this actually works. And for suppose I will take one example here. I will be drawing a big graph of sin x like this thing. Suppose this is the curve of sin x from 0 to 2 pi. And suppose this is the mark corresponding, you know very well, this is the mark corresponding to plus 1, this is the mark corresponding to minus 1. Now suppose I wish to take a point here. Suppose this is the point here. Suppose this is some point here. This is, now, this is some, this is, this is pi mark, this is 2 pi, and something like this thing. So some number between pi and 2 pi we have chosen. And now I had to show you that yes, at this particular, what is the value, and suppose, okay, let me, instead of this thing, suppose, let me show here. Suppose this is something, this is pi by 2, and this is something, say, 40 degree or 50 degree, whatever. So suppose this is A, and this is what? Sin A. This is the mark corresponding to sine of A. And then what you need to do? You take some sin A plus epsilon and sin A minus epsilon. Because what you will claim that limit x tending to A sin x, you have to show this is nothing but sin A. So what you will do? See, you will consider here this two lines, okay, this is 0, this is, suppose A is some number here, and sin A is some number, say, here, sin pi by 2 is here, suppose, this is your sin A. Then suppose you have chosen some epsilon, neighborhood of A plus epsilon, A minus epsilon here. This is your sin A mark, suppose, sorry. This is your A, this is sin A, suppose. This is sin A mark, and this is sin A plus epsilon mark. This mark, and this is the mark corresponding to sin A minus epsilon. And this middle mark is sin A. Okay, so this I am showing over here. Now I have to find, see, for this A I have to find a delta. How this delta is to be found? Please see what I will do. This corresponding to sin A, I will draw one line and I will see where it intersects my curve. It is intersecting at this particular point. Okay, I will draw it. where this line intersect this line. This line will intersect this line. Let me write this line. Suppose this is point say a plus x1, and this is the mark corresponding to a minus x2. That is, this distance is say x1 and this distance is x2. See, please see. What I have done, from this sin A, this is the middle mark. Sin A plus epsilon, I will draw a line, horizontal line, wherever it cuts the curve of sin A, and from there I will draw it. Say this is a plus x, so that is the distance a plus x1. It is a plus x1, this is a plus x2. So this much of distance will be x2. Now see what I do. I take a number x naught which is less than x1 and x2 both. x1 and x2 both. Please see, I have chosen a number x1 and x. Suppose x1 is say 0.5. This is 0.4. So I will choose a number which is less than 0.4 and 0.5. Say 0.3 is the number, and that number I am denoting by x naught. So what I will do? My required delta will be this x naught number. Now see, my contention is what? That my required delta for this epsilon, suppose this epsilon which I have chosen here, see, for this epsilon, how this delta is to be found? This will be a number, this is x1, this is x2. So x naught is something which is at the equal distance here. This mark is corresponding to a plus x naught, and this is mark is a minus x naught. This interval a minus x naught, a plus x naught, this deleted data node we will take. This set will be contained wherein? This will be contained in a minus x2 and a plus x1. A plus x1. This is a subset. This is a subset of this set. And so what are x1, x2? x1 and x2 are the numbers which I will obtain in this particular fashion. That this I will draw. Here I will take, this is a plus x1, suppose number on abscissa, and this is a plus x2, implying that a minus x2, so that this is x2 distance, this is x1 distance. So any number which is less than x1 and x2 both can be taken to be my required delta, for the obvious reason, because if my this now in here x lies somewhere here, suppose here, so see that where my this functional value will lie here, and which will be in the epsilon neighborhood. Please see, in this neighborhood you choose x anywhere, and you can easily show this side that this is you have chosen, and then see what you are finding it, that this is the value. Again see, it is between sin a plus epsilon and sin a minus epsilon. So see, graphically you can show that yes, this is one graphical method of finding delta for all the continuous curves. For all the continuous curves. See, you must say that what will be the, how this thing? Okay, suppose this is the point here. This is the point what? Suppose this is 3 pi by 2. This is 3 pi by 2. How you will show? 3 pi by 2 is this mark, okay? And here see, simple. 3 pi by 2, it is this mark. That, sorry, sine 3 pi by 2, that is minus 1. So it is minus 1 basically. So you take any small interval, this way, this way. Now here when you will draw, of course, see, it will cut here. Okay, so this is, say, this is, what is it, 3 pi by 2. So this mark is what, how much? This is 3 pi by 2, this must be something, whatever you write, 3 pi by 2 minus, say, x1. And for this thing, see, it will never cut the graph. It will never cut the graph. So don't bother about it. What you will see, if it is not getting, it will not come also. So what you need to do is that you can take any interval here. Here, simply say that this 3 pi by 2, because see, the value will never go beyond this thing. Minus 1 plus minus epsilon is this thing, minus 1 plus epsilon will be this mark, isn't it? So here the value will never lie in this interval between minus 1 and 1 plus epsilon. So what you need to do is, you can simply take this much of interval. This much of interval will suffice, isn't it? Because 3 pi by 2 mark you have to take in. So what you need to do is, so this much of distance, sorry, this much of distance will be x1, isn't it? And So what you need to do, because see, you have to simply show that this is lying here. So you simply say that your required delta is this much, x1. Because here if you are taking x1 also, then no issues. It will be lying this side. It will never go beyond this. Because see, this line will intersect like this thing. So it is x1 or say it is x2, suppose. So one way is that you take less than x1 and x2 both. Delta is less than x1 and x2 both. So that will also suffice. Because once you take less than this thing, so the values will fall where? In this interval only. In this interval only. Wherever you take, they will go here only. So this is how you can always ensure. For continuous curve, see, it won't be a problem. So today I end up here, with hope and expectation that you will go through this definition. Then we will come to another definition which is given not in the geometrical manner, but it is given in a more. There won't be much difference. If you can understand this definition, then that is almost a automatic offshoot of it. There will be hardly any difficult. Same rephrasing, but of course that we, instead of saying that fx falls within this epsilon neighborhood of L, we will say that fx minus L is less than epsilon. So that's all. So with this, I hope that you will revise the things. We will again meet on Monday. Thank you.